Okay, well, during the next few minutes, I'd like to explain to you how we determine the temperature in the lithosphere from heat flow data, and what determines mantle temperature, not only the surface heat flow, but mostly the vertical distribution of heat-producing elements. Since I've heard the take-home message from Alan, okay, I'm going to also introduce different data sets to constrain our temperature model. I'm going to briefly talk about xenolith and mostly talk about shear wave velocity profiles, or how we can use shear wave velocity profiles to better constrain our thermal models of the lithosphere. I'm going to take a very pedestrian approach, so I hope you can stay awake for until coffee. So, well, let's first look at the continental heat flow map. Okay? And what it shows essentially is that cratons that you see here in blue are cold. The Siberian, Baltic, Australian, South Africa, West Africa, Canadian Shield are all cold regions on this heat flow map. And for a long time, it was thought that, well, there was nothing much about heat flow in cratons. Cratons are cold and characterized by a cold geotherm. And that was the end of the story. Well, if it was the end of the story, I would not be sitting there. You'll have to wait a few more minutes to get to the end of the story. Now let's look, I'm going to focus on North America, and this is the heat flow map of North America, and just to point out, there is a large contrast between the eastern part and the western part, both on the ocean and in the continent. The margin, the Pacific margin is young and hot. The Atlantic margin is old and cold. The western part of North America is active and hot, and nothing much happened in the eastern part of North America that is very cold. Okay. Canada is coldest, and I'm going to focus on Canada. Okay. And this is the region I'm going to focus, essentially the southern part of the Canadian Shield. Okay. Very briefly, to give you a brief overview of the architecture of the Canadian Shield. The Canadian Shield is made up of Archean craton. This here is a superior craton, different belts that were amalgamated at 2.5 billion years. There are other cratons, the Hearn-Ray, the Slave Craton to the northwest. There is the Nain Craton here, and all these cratons were welded together at 1.8 billion years by the trans-Hudson origin that you see here, and that continues under Hudson Bay. Just going to point out, because I'm going to mention the geography a little bit later, this is James Bay, the little appendix at the base of Hudson, or south of Hudson Bay. To the south of the Archean cratons is the Grenville province, which is a lot younger, 1.1 billion years, and then you see the Appalachians there. Now, why am I focusing on Canada? It's not only because I have a deep love for Canada, but mostly because we have a lot of heat flow data, and the heat flow data are represented here by black dots, and you see that there are plenty of heat flow data in here, in there. Okay. Heat flow data, also we have heat production data. We measure the heat production we measure the heat production with the heat flow at all those sites, so that we can correlate the surface heat flow with, or try to correlate surface heat flow with the crustal heat production. Okay? Now, how do we calculate temperature from that? Okay. Well, we solve the steady-state heat equation. We assume we are looking on regional averages. So we assume that we are looking at temperature on a horizontal scale of a few of 100 kilometers or a couple of 100 kilometers to compare with the lithospheric thickness. Okay. And what will determine temperature then is this steady-state one-dimensional heat equation. Okay. We have here the thermal conductivity, which we assume we know from laboratory experiments, and we have the vertical distribution of heat-producing elements, or vertical distribution of heat production. Okay. All we know is surface heat flux. How do we determine how heat production varies with depth? When we have parameterized the heat production, okay, in this way, we have the surface heat flow. We assume that mantle heat flow is mantle heat production is relatively small, and actually what we worry most about is the heat production in the crust. So basically, the heat production, the mantle heat flux is going to be equal to the surface minus heat production in the crust. Okay. Heat production in the crust varies vertically, and the way we characterize this heat production in the crust is by looking at a parameter that we call differentiation index that tells you how much the upper crust is enriched relative to the lower crust. So we measure the average upper crustal heat production. Okay. And compare with the average total crustal heat production, vertical average of the heat production. Okay. And these are the three parameters that we are going to use to try and determine temperature profiles. How do they affect the temperature profiles? Here you see we have calculated different temperature profiles with keeping the mantle heat flux constant and varying surface heat flux between 30 and 75 milliwatts per square meter. That's fairly high for shield area. We have observed values as high as 80 milliwatts per square meters, but they are really freak values. Standard values in the shield will be between 25 and 55 milliwatts per square meters. Okay. But you see that the range of geotherm that we can have by varying surface heat flux. Okay. In this case, we have crustal heat production uniform. What happens if we vary the crustal differentiation index? The crustal differentiation index that we have measured or determined vary from 0.7, which is quite strange, to 2.2 in the Slave Province. You see, we also get a range of geotherm, a much narrower range that we obtain by varying the surface heat flux. Okay? But the third thing that we can vary is the Moreau heat flux. In other words, that amounts to varying also the total crustal heat production. Okay? And here we see three geotherms with the same surface heat flux, 45 milliwatts per square meter, which is an average heat flux for the shield. Okay? And you see that varying the Moreau heat flux by plus or minus 3 milliwatts, these are milliwatts, these are watts per square meter, but varying by plus or minus 3 milliwatts per square meters makes a huge difference in the mantle temperature. And actually, the most important parameter in determining the mantle temperature is not really the surface heat flux, Okay? But it's what is the heat flux at the base of the crust, okay? What is the temperature gradient, which determines the temperature gradient in the mantle. And 3 milliwatts per square meter, okay, makes a hell of a difference that we can not really resolve from surface heat flux and heat production data. So we have, just a brief word, we have tried to determine how mantle heat flux varies, okay, from in stable continents. This should be really the shield. Okay. One constraint on mantle heat flux, of course, comes from the lowest heat flux value that we have at the surface, okay, and lowest values that are measured are about 20 milliwatts per square meter. Some lower values have even been reported, but if we look at regionally average values, these would be about 22 milliwatts per square meter. So mantle heat flux must absolutely be lower than this. Okay? Our best estimates come from region where the entire crust has been exposed at the surface and has been sampled. By sampling the heat production in the crust along these crustal sections, okay, we have obtained estimates of 13 to 15 milliwatts per square meter for the mantle heat flux. Okay. Another way is to look at the Granville province that I mentioned before. In the Granville province, we have different different crustal levels that have been exposed at the surface, and by sampling the heat production at the surface, we sample all crustal levels, and averaging the surface heat production in the Granville province, horizontally averaging, gives also a good vertical average of the heat production. Okay? So in that way, we also have obtained 13 milliwatts per square meter. And then we have done some modeling of gravity, crustal thickness, seismic refraction data, and try to invert simultaneously all these constraints, and we get 30 milliwatts per square meter. Okay? The conclusion is that, well, heat flux should not vary by more than plus or minus 3 milliwatts per square meter, but it makes a hell of a difference. So to better constrain, we'll have to use other data sets. I'm going to briefly show some xenolith data from the Canadian Shield. Okay? And we have here two sets of xenoliths that we have plotted. The results there would be well, pressure converted into depth for and temperature for Kirkland Lake, which is in the Superior Province, just in the center of the Superior Province. And then we have xenoliths from the Slave Province to the northwest, okay, that appear to be colder. Okay. Although, which is interesting, the surface heat flux is higher in the Slave than at Jericho than at Kirkland Lake. Okay. The other thing that you can see is that both sets actually are fairly well modeled by geotherms, okay, that are more or less parallel in the mantle, indicating that once again we probably have the same mantle heat flux in both these regions. Okay. So the next step, well, this is the heat flow map that I showed before, is was to compare heat flow with seismic data. And here, what we have used is the surface wave tomography models of Susan van der Lee and Heather Bedell. Okay, that you see here, this is the surface wave, the shear wave velocity anomaly at 150 kilometers from surface wave tomography. Okay? You see, well, there is a good correlation between heat flow and surface wave tomography data. Okay? And we are going to try and use this to better constrain, okay, the mantle temperature from the surface wave tomography data. If we are going to focus on the southeastern Canadian shield, as I said before, and this is the map of the heat flux in the surface heat flux in the southeastern Canadian shield. And you see there is quite a bit of variability. We have both small short wavelength variations in surface heat flux that are essentially due to variations in surface heat production. Okay? But we also seem to have long wavelength trends with increasing or decreasing heat flux to the north of the superior province, and possibly, okay, a decrease in heat flux to the east, from the western to the eastern side of James Bay. Okay? Now, the shear wave velocity anomaly, when we focus on this region, do not at all show the same thing. I mean, it's a lot more uniform in the shear wave velocity anomaly at 150 kilometers. Now, actually, what we can do from the temperature profile, we can also try and determine how shear wave velocity varies with depth. And you see here, we see, these exemplifies what I showed before, that surface heat flux may be important, but the variation in mantle heat flux are as important in determining small variations in mantle heat flux may be more important in determining these surface velocity, the shear wave velocity profiles as the large variation in surface heat flux. And these variations can probably be resolved by the by the shear wave velocity profiles that have been inverted, obtained by surface wave tomography. Here we see three shear wave velocity profile from 60 to 300 kilometers. Okay, this one seems a little bit pathetic, but the other two look very much like the profiles that we have obtained from the temperature profile. So we could try and invert those profiles for determining the thermal parameters for modeling mantle temperature. Okay? So what we are going to try, what we have done actually, is to do a Monte Carlo inversion of these vertical velocity profile, okay, together with the surface heat flux. Okay? So in the inversion, okay, we have some free parameters for calculating the temperature profile. Actually, we are going to let the surface heat flux vary because there is some variability in the surface heat flux, and probably the regional average is determined to no more than plus or minus 4 milliwatts per square meter. Okay? We are letting mantle heat flux vary. That determines crustal heat production. We are going to let the differentiation index vary, okay? And we are also letting mantle heat production vary, although we do believe that its mantle heat production is small. Okay? Crustal thickness is always constrained by seismic fraction when available, or by some receiver functions analysis. Okay? And we have used different composition to convert temperature into velocity. Essentially, we have used both McDonough and Rudnick and Griffin models of composition. Okay. This is an example of a good fit. Okay. This is these are the data from the surface wave tomography. I shouldn't say data, but these are the these are the velocity from surface wave tomography, and this is our temperature, the profile from our temperature model that fit, or the average temperature model that fit the surface wave tomography. We did a Monte Carlo inversion, so what we get, okay, are histogram of value of parameters that fit the model. And the one thing that we can see here, okay, is that actually the only one parameter that is really well fit, okay, is mantle heat flux. Okay. This is really very strongly constrained, and we get 13 or 14 milliwatts per square meter from here. I cannot tell. Okay. The other parameters are much less constrained, and actually there is a range of value of surface heat flux, mantle heat production that could fit the data. This is a site west of James Bay where surface heat flux was 34 milliwatts per square meter. Okay. We can look at a different site. Now we are east of James Bay, where surface heat flux, mean surface heat flux, is 28 milliwatts per square meter. This is our best fitting model. Okay. The fit of the velocity profile with the data. And again, we see that mantle heat flux is fairly well determined, and we get 15 or 16 milliwatts per square meter, slightly higher, although the mean surface heat flux is a little bit lower. Okay. So that's the story, and we can put all this on a map, okay, where we see the average mantle heat flux, or the mantle heat flux that we have obtained, okay, from this inversion. And you see that on the map, actually, it seems that I was hinting that heat flow was a little bit lower in this region. The mantle heat flow seems to be a little bit lower in this region than in the region east of James Bay. Okay. The average mantle heat flux for the superior province is 14.5 milliwatts per square meter, and standard deviation is very small, 1.3. So this is something that seems to be extremely well constrained. Wrong. Okay. We can also try and determine lithospheric thickness from this type inversion, and again, we seem to see a thicker lithosphere, okay, in the west of James Bay, or the western part of the superior province, than in the eastern part of the superior province. The average lithospheric thickness for the superior province is 225, with a very small standard deviation again, plus or minus 15 kilometers. Okay. So, and we could do the same for the Granville province. Not surprisingly, we have the same value of the mantle heat flux for the Granville province, the same mean, the same standard deviation, and the same lithospheric thickness for both these provinces of the Canadian Shield. Okay. So, in conclusion, well, it works. Putting together surface heat flux and shear wave velocity profiles seem to help in determining reasonable vertical velocity, vertical a temperature profile and a vertical velocity profile for the region. Okay? This gives us very strong constraint on Moreau heat flux. Okay? The central value of Moreau heat flux is plus or minus 15 milliwatts per square meter. Okay? And this is consistent with all the estimates that we had before, but I think we narrowed down the variability around this value. Okay? Lithospheric thickness 220, let's say plus or minus 25 kilometers. Okay? And lowest mantle heat flux, thickest lithosphere do not always coincide with lowest surface heat flux. So what you see is not really always what you get. Okay? Now, is that the end of the story? I mean, it's not quite the end of the story. I still would like to see a little bit more, resolve a little bit more what's happening between the eastern and the western part of James Bay. Okay? And then there is the other part of the Canadian Shield that we have not analyzed yet, which is the Trans-Hudson origin, where it seems, both from the heat flux and from the surface wave tomography data, that the lithosphere is thickest. So that's the next step in this never-ending story. Thank you.